Hello everyone. Now we are recording Codechef Starter 212 Interesting Binary Easy Version Solution. The problem name is Interesting Binary Easy Version. Let's understand the problem statement. The problem gives us an array of size n. It's a binary array consisting of only zeros and ones. Alright? They're asking us to perform some operations on this array such that adjacent elements are not equal. Okay, what do we mean by that? Let's take an example. The example is 0, 0, 1, 0. Okay. This is a binary array that is given to us. We are asked to perform some operations on this array such that the resultant array does not have any adjacent elements equal. Okay. The operation that we can perform is we can choose any index in the array and we can increment that value. Okay, we can choose any index in the array and increment the value. So over here, the easiest way in which, or the most cost efficient way of making adjacent elements not equal is choosing index 0. After choosing index 0, we can increment it to 1 and it becomes 1 0 1 0, where adjacent elements are not equal, right? So we are asked to find the minimum number of steps the minimum number of operations needed to make adjacent elements not equal. Alright. Now, in order to find this minimum number of operations, we need to make some observations. What are these observations? We will be given a binary array consisting of zeros and ones. We are asked to increment any index such that we achieve this criteria. Adjacent elements are not equal, right? Now, when we are incrementing, right, we should understand till what element should we increment. Should we increment once? Should we increment twice? Should we increment thrice? And where should we stop, right? In order to understand that, I'll be taking an example where after incrementing, we get a resultant array. Okay. Let's assume that this is our resultant array. 1, 2, 1, 2, 5, 2, 1, 2, 0. Alright. This is not the given array. This is the resultant array where after incrementing the values, we got a resultant array where every adjacent element is not equal. Okay, we don't know how many operations we performed. We don't know that. But this is the resultant array we got. Alright. Now, is it necessary to make all these changes, or can we do it in less changes also, is what we need to figure out. Alright. We initially got an array which contained only elements zeros and ones. There was no 2, there was no 5, right? But after making some increments, we got some 2s and some 5s. What I'm trying to do is, let's try to make sure that this array, do we even need this 5, or can we solve this in less than 5 element, is what we need to figure out. See, instead of keeping 5 here, instead of incrementing till 5 at this particular element, I can say that we could have stopped it at 3 itself, because anyhow this 2 and this 3 are not equal, this 3 and this 2 are not equal. So keeping it as 5 is as good as keeping it at 3, right? In less cost, we'll be able to get 3, right? So instead of going till 5, I would say one reduction that we can do is stop it at 3 itself. All right. But is even 3 required? Let's see. If I want to reduce this 3 even further down to 2, can I do it? Yes or no? Let's try to figure out. If I reduce it to 2, then it coalesces with towards left side, it collides with towards right side also, right? So what can we do then? Well, we could have reduced this 2 to 1, right? This 1 that we have on the left side of 2, that could have become 2. This 2 that we have on the left, that could have taken as 1. All right. This 1 that we have on the left, that could have been 2. All right. If we do this change, then instead of 5 over here, we could have had 2 in this place as well. You might argue, sir, we have 2 right over here, right? What if this 2 was the original value? We cannot reduce the value. We cannot reduce the original value. We can only increase it, right? Yes, that's true. So instead of reducing this 2, right, we could have reduced this 5 to 1. Maybe the original value itself was 1, right? Then if the original value was 1 over here, then on the left side there is a 2, on the right side there is a 2. The adjacent elements are anyhow not equal, right? So this is also a possibility, right? So what we are trying to conclude here is that we don't need elements like 5, 6, 7, 10 into our resultant array. Whatever array they give us, the resultant array will have elements in the range of 0 to 2 only. Okay. Now let's take a few more examples to actually understand this claim that I'm making. Right? Let's take one example, which is 1, 1, 1, 1, 1. All are ones. Right? Now, in order to make adjacent elements not equal, I can either pick this guy, make it 2. I can pick this guy, make it 2. I can pick this guy and make it 2. Adjacent elements are not equal, right? Here the elements are all in the range of 1 to 2. If I take a different example, let's say 0, 0, 1, 1, 1, 0, 1. If I take this example, then I can take this index 0, increment it to make it 1. Here we have 3 ones together. We can take this index, make it 2. Then that's it. We don't have any more adjacent elements equal, right? So with these examples, we can actually conclude that our resultant array will only have elements in the range of 0 to 2. We don't have any other element outside this range in the resultant array, right? Now they are not asking us the resultant array. What are they asking them? They are asking us the minimum number of operations needed to make the adjacent elements not equal. All right. So in order to understand this, you need to understand that every element in our array actually has 3 possibilities. Either it can be a 0, or it can be a 1, or it can be a 2, right? Now this is not true for every single element. Why? Because if original value of the element itself is 1, it cannot go back to 0. That's not possible. You can make it 1 or you can make it 2. But still, we cannot go beyond this. If any element is 0 initially, it can either be 0, become 1 or become 2. That's possible. If initially one element is 1, it cannot become 0 for sure, but it can become 1, it can become 2. That is possible, right? So what we need to do is we need to remember what will happen if this element ends up being a 0. How many steps are required? What will happen, or how many steps are required if this element ends up being a 1? What will happen, or how many steps are required if this element ends up being a 2. All right. We have to do this for every single element in the array. You might ask, why? Because every single element is dependent on other elements. Like, for example, if I decide to keep the first element as 0, then the next element can't be 0, right? Over here in this array, the above array, the second element is 0, but it cannot be 0. So I'll have to make it 1. Why did we decide to make it 1? Based on the previous element's decision. So if I want to represent the states of each and every element, like how many modifications or operations are required to keep the current element at 0, to keep the current element at 1, to keep the current element at 2, then we will have to write a relation between the previous elements, right? For example, let's say your array is A, right? A is the array, and in this array, if I want the element at index I to be 0, then what all changes do we need to make? Like, what are steps required, or in how many steps can we make sure that this element will be at index this element at index I will be 0? It actually depends on the previous element, right? So A of I minus 1, when the previous element is 1, right? This term tells us that if the previous element was a 1, then how many steps were required so that previous element reaches 1, right? Plus number of steps needed for the current element to reach 0. With this, we'll be able to figure out in how many steps our current element, the ith element, will become 0, right? But the previous element should be 1 only is not correct, because the previous element can be 2 also, because as we have just now seen that there are 3 possible states for any element. It can either be 0 or 1 or 2. So previous element cannot be 0. It can either be 1 or 2. So the other possibility is, if the previous element reaches 2, right, then A of I minus 1 comma 2 tells us that the number of operations that are needed for the previous element to reach 2, okay, plus the number of steps needed for the current element to reach 0. Okay. So the minimum of these two conditions or these two values will actually tell us the number of steps required to reach 0 at index I. Okay. Now this we need to find for A of I comma 1 also. We need to find for A of I comma 2 also, right? And we need to do this for every index in the array, so that by the time we reach the n-1th index, we have 3 values. What are they? A of n-1 0, A of n-1 1, and A of n-1 2. What does these values represent? A of n-1 0 represents the number of steps needed for the last element to reach 0. What does this represent? A of n-1 1 represents the number of steps required for the last element to reach 1. And A of n-1 2 represents the number of steps required for the last element to reach 2. Right? Out of these 3, whatever is minimum will be our answer. Right? Now, it's not always possible that an element can reach 0 or an element can reach 1. Why? Because imagine if the original value of that element is itself 1, right? If the given array contains 1 at a particular element, particular position, then this guy cannot be converted into 0, cannot be converted, right? Why? Because there is no decrement operation provided, there is only increment operation. So if we want to find out the number of steps needed for this index to reach 0 or to become 0, then this will be infinity. This will be infinity, which denotes that it's not possible to reach 0. And on the other hand, if we want to reach 1, we can find out using these relations. If we want to make it 2, we can find out using these relations. And out of these 3, whatever is the minimum will be our answer. Okay. So if I have to write a general statement where a of I j, where I is the index in the array and j is the value that we want to store, then this actually boils down to 3 conditions. Not 3 but 2. That is, if the previous element a of I minus 1 comma k plus the number of steps to reach from current value of a of I to j. Okay. What is this k? This k is the possible values that a of I minus 1 can be at. If j is at 0, then k can either be at 1 or 2. If j is 1, then k can be either at 0 or 2. If j is 2, then k can be either at 0 or 1. So out of these possible values of k, we need to find at which value of k we have minimum number of steps. To those steps, we will add the number of steps to reach from current value to a of I. Current value of a of I to j. Okay. Current value can be 1 and current value of a of I can be 1. If j is 2, we need 1 step. If current value of a of I is 0 and j is 2, we need 2 steps, like that. Okay. But here, in order to find all these values, there is one cell for whom previous cell doesn't matter, and that cell is the 0th index. For the 0th index, you don't need to depend on the previous index value in how many steps the previous index reached a particular state. We don't need to do that. So a of 0 comma 0, a of 0 1 and a of 0 2 actually depends on the current value. Okay, so a of 0 value, if a of 0 value is 0, then the number of steps needed to reach 0 is 0. If a of 0 value is 0, the number of steps needed to reach 1 will be 1. If a of 0 value is 0, the number of steps needed to reach 2 is 2. Right? But if a of 0, original value of a of 0 is 1, then it is not possible to reach 0. That's why it's infinity. If a of 0 value is 1, the number of steps needed to reach 1 is 0. If a of 0 value is 1, number of steps required to reach 2 is 1. Okay. Similarly, you will find the value for a of 0 equal to 2. If a of 0 was 2, it's impossible to reach 0. It's impossible to reach 1. And the number of steps needed to reach 2 will be 0. Okay, that's how you will find the different number of steps needed to reach 0, 1 and 2. At the end, you have to find the minimum of a of n minus 1 0, a of n minus 1 1, and a of n minus 1 2. The number of steps needed for the last element to be 0, the number of steps needed for the last element to be 1, the number of steps needed for the last element to be 2. The minimum of all these three will be our answer.